Something is happening to the American summer that goes beyond uncomfortable. It goes beyond the kind of heat that sends people inside for a few days and then breaks with a thunderstorm and cool air rolling in from the north. What is being documented now, in the soil temperatures, in the overnight lows that refuse to drop, in the heat indices that push past 120 degrees Fahrenheit in cities that were never supposed to feel this way, is a structural transformation of the thermal regime across the continental United States. Not a bad stretch of weather, a shift in the baseline. The difference between a bad year and a new normal is precisely this. When conditions stop being aberrations and start being what you plan around, what you build for, what you warn your children about before they go outside. That transition is happening right now, documented in datasets from the National Oceanic and Atmospheric Administration, in emergency room admissions records, in power grid strain reports from the Southwest, and in the bodies of people who are dying from heat at rates that were not seen 20 years ago and were not modeled to arrive this soon. The heat dome phenomenon is the specific atmospheric mechanism responsible for the most extreme events, and understanding it is essential for understanding why the pattern feels so different from ordinary summer heat. A heat dome forms when a high-pressure system stalls over a region, trapping hot air beneath it like a lid over a pot. The sinking air in a high-pressure system compresses and warms as it descends, a process called adiabatic warming, and simultaneously suppresses cloud formation, allowing maximum solar radiation to reach the surface. This is basic atmospheric physics, not a new discovery. What has changed is the frequency, the duration, and the geographic extent of these systems. The June 2021 heat dome over the Pacific Northwest, a region culturally and architecturally unprepared for extreme heat, pushed temperatures in Portland, Oregon to 116 degrees Fahrenheit and killed an estimated 700 people in Oregon and Washington over the course of 3 days. That event was later determined by climate attribution researchers at World Weather Attribution to have been virtually impossible without human-caused climate change. The statistical estimate was that such an event would occur roughly once every 1,000 years in a pre-industrial climate, compared to roughly once every 5 to 10 years in the current climate. That single attribution study, one of dozens produced each year now, contains within it the core of what is happening to America's thermal landscape. The urban heat island effect amplifies the baseline warming in ways that are measurable, mapped, and in most American cities, profoundly inequitable. Cities are warmer than surrounding rural areas because of the dense concentration of heat-absorbing surfaces, asphalt, concrete, dark rooftops, combined with reduced vegetation, reduced evapotranspiration, and direct heat generation from vehicles, air conditioning units, and industrial processes. The differential between an urban core and its suburban periphery can exceed 15 degrees Fahrenheit on a calm, sunny summer night. That differential matters most precisely when it matters most: overnight. The human body's ability to recover from daytime heat stress depends critically on nighttime cooling. The core body temperature needs to drop during sleep for physiological recovery to occur. In cities across the American South and Southwest, overnight lows that were once in the low 70s are now regularly in the mid-280s. Data was filling to appeared warmer with its only of cities, and such as the own low differences as low lows that were now mid. Phoenix, Arizona recorded its hottest night in history in July 2023, with the overnight low failing to drop below 90 degrees Fahrenheit. For the approximately 14% of Americans who lack home air conditioning, a number that rises sharply in lower-income neighborhoods, this is not a statistic. It is a medical condition developing in real time, every night, across multiple consecutive weeks. The geography of extreme heat in America is not uniform, and the regional patterns tell a story that is both predictable from physics and surprising in its specific manifestations. The Southwest has long been hot, but the combination of record-breaking temperatures with the worst drought in 1,200 years, documented through tree ring analysis and lake sediment cores, is producing compound hazards that amplify one another. Soil moisture deficit amplifies surface heating because dry soil cannot release heat through evaporation. The latent heat that would have cooled the surface instead stays as sensible heat, raising temperatures further. This feedback loop is well documented in the literature, and its effects are measurable in the temperature records. Parts of the Southwest that were already at the upper limit of human thermal tolerance are now regularly exceeding those limits. The Colorado River, which supplies water to approximately 40 million people across 7 states, has been running at roughly half its historical average flow for the past 2 decades. Lake Mead and Lake Powell, the 2 largest reservoirs in the country, dropped to historic lows in the summer of 2022, triggering the first ever federally declared water shortage on the Colorado River system. Heat and drought are not separate problems in the Southwest. They are the same problem viewed through different instruments. The Southeast presents a different thermal challenge, one driven by the particularly brutal interaction of high temperatures with high humidity. Heat index, the perceived temperature accounting for humidity's effect on the body's ability to cool itself through sweat evaporation, regularly exceeds 115 degrees Fahrenheit across much of the Gulf Coast region during summer months. The physiological mechanism behind this number is straightforward. Sweat cools the body only when it evaporates, and evaporation becomes inefficient when the air is already heavily saturated with water vapor. At a wet bulb temperature above approximately 35 degrees Celsius, roughly 95 degrees Fahrenheit at 100% humidity, the human body cannot cool itself through sweating even with unlimited water intake, even in the shade, even at rest. Prolonged exposure above this threshold is fatal for healthy adults. The good news, such as it is that sustained wet bulb temperatures at this level remain extremely rare even in the current climate. The concerning news is that the number of hours per year during which wet bulb temperatures approach this threshold in parts of the Gulf South is increasing measurably, and the models project continued increases through mid-century under all emission scenarios currently considered plausible. The Midwest and Great Plains are experiencing a heat transformation that receives less media attention than the Southwest or Southeast, but is arguably more consequential for the national food supply. The Corn Belt, the region stretching from Ohio through Indiana, Illinois, Iowa, and into Nebraska, that produces a substantial fraction of the world's corn and soybean supply, has warming growing seasons and more frequent heat stress events during the critical pollination periods. Corn is particularly sensitive to temperatures above 92 degrees Fahrenheit during the week of pollination. At temperatures above this threshold, pollen viability drops sharply and yield losses follow. Research published in Nature Food and elsewhere has documented a consistent relationship between extreme heat events during pollination and yield losses at the county level across the Corn Belt. The trend in extreme heat days during the growing season in this region is upward, and the relationship between those days and food prices is direct and measurable. When the Corn Belt stresses, food prices rise globally, because American corn and soybeans are traded in global commodity markets. The thermal transformation of America's agricultural heartland is not a domestic story. The health burden of rising heat in America is being quantified with increasing precision, and the numbers that are emerging are larger than most people who are not specialists in this area would expect. A 2023 study published in Nature Medicine estimated that approximately 61,000 deaths in Europe were attributable to heat during the summer of 2022, one of the hottest summers in European recorded history. The methodology used in that study, when applied to American data, produces comparable estimates for extreme heat summers in the United States. The Centers for Disease Control and Prevention reports approximately 700 heat-related deaths annually in the United States based on death certificate data. But this figure is widely acknowledged by researchers in the field to be a severe undercount, because heat is rarely listed as a primary cause of death when it acts as a trigger for cardiac events, respiratory crises, or kidney failure in people with pre-existing conditions. Epidemiological studies using excess mortality methods, comparing observed deaths during heat events to expected deaths based on historical baselines, consistently find heat-attributable mortality that is 3 to 10 times higher than the official certificate-based counts. The true annual toll of heat-related mortality in the United States is likely in the thousands, and possibly in the tens of thousands in extreme years. The people dying from heat in America are not randomly distributed through the population, and this is a fact that the data makes impossible to avoid. The elderly are disproportionately vulnerable, both because thermoregulatory capacity declines with age and because older Americans are more likely to live alone, in older housing stock without central air conditioning, in urban neighborhoods that have lost population and investment. People with certain medical conditions, cardiovascular disease, chronic kidney disease, diabetes, psychiatric conditions requiring medications that impair thermoregulation, are at substantially elevated risk. People working outdoors, agricultural workers, construction workers, landscape workers, delivery workers, are exposed in ways that no amount of individual precaution can fully mitigate when ambient temperatures are extreme. And across all of these categories, race and income function as multiplying factors because lower-income households and communities of color are more likely to live in urban heat islands, more likely to lack home cooling, more likely to hold outdoor jobs, and less likely to have access to healthcare that would treat heat-related illness before it becomes fatal. A study published in Nature in 2021 found that formerly red-line neighborhoods in American cities, areas systematically denied investment for decades under discriminatory federal housing policies, are on average 5 degrees Fahrenheit hotter than non-red-line neighborhoods in the same city, with less tree canopy and more impervious surface. The thermal geography of American cities is not an accident of physics. It is, in significant part, an artifact of policy choices made generations ago. The infrastructure challenge posed by rising heat is substantial and largely unaddressed at the scale required. The American electrical grid, a patchwork of regional systems built primarily in the mid-20th century, was not designed for the peak demand loads that multiple simultaneous extreme heat events now impose. When temperatures exceed 110 degrees Fahrenheit across a large region for an extended period, demand for air conditioning exceeds the design capacity of distribution systems, and transformers, which are expensive, slow to manufacture, and difficult to replace, begin to fail from thermal overload. The Texas grid failure in February 2021 was caused by extreme cold, but the summer peak demand problem in Texas is equally serious and growing. The Electric Reliability Council of Texas has repeatedly issued conservation warnings during summer heat events as demand approached system capacity. The Pacific Southwest grid faces similar challenges. As California and Arizona simultaneously experience extreme heat, the transmission capacity between the two states becomes critical, and both states need power at the same time. The capital investment required to harden the American grid against extreme heat, upgrading transformers, adding redundant capacity, expanding transmission, deploying distributed storage, is measured in hundreds of billions of dollars. The spending that has occurred is a fraction of that. The gap between what the infrastructure needs and what it is receiving is a source of serious concern among engineers and grid operators. The wildfire interaction with heat is a compounding factor that is reshaping the physical environment in ways that then feed back into the heat problem. Wildfires are driven by the combination of drought, heat, and fuel accumulation, and the American West is experiencing all three simultaneously. The wildfire season that was once a seasonal phenomenon confined to late summer and fall has in many regions effectively become a year-round condition. Fire consumes vegetation, replacing tree canopy with dark, burned surfaces that absorb more solar radiation, driving local temperature increases. Fire smoke reduces air quality across enormous regions. The smoke from West Coast wildfires in 2020 and 2021 reached the East Coast and was detected in Europe, affecting air quality across hundreds of millions of people. The combination of extreme heat and wildfire smoke creates a compound public health emergency in which people who would otherwise manage heat by outdoor activity are forced inside by dangerous air quality, while people without adequate housing or air conditioning cannot effectively stay inside. The feedback between heat, drought, fire, and further heat is a reinforcing cycle that is accelerating the rate of environmental transformation across large portions of the American landscape. The attribution science connecting these events to human-caused climate change has become increasingly precise and increasingly rapid. The World Weather Attribution Group, formed in 2014, has developed methodology for attributing individual extreme weather events to climate change within days or weeks of the event occurring, fast enough to be policy relevant while events are still in public consciousness. The basic logic of attribution studies is straightforward. Researchers run large ensembles of climate model simulations, comparing the probability of an event in a world with observed greenhouse gas concentrations against the probability in a counterfactual world with pre-industrial concentrations. The results are expressed as probability ratios. This event was X times more likely in the current climate than in the pre-industrial climate, and as changes in intensity. The June 2021 Pacific Northwest heat dome was found to be about 5 degrees Celsius more intense due to climate change. The summer 2023 heat across the American South, which broke records across multiple states, was found to be virtually impossible without human-caused warming by multiple attribution analyses. These are not model projections of future events. They are quantified assessments of events that already happened, using methods that have been peer-reviewed and cross-validated across multiple research groups. The projection forward from the current baseline is where the phrase, "only the beginning," in the title of this piece, draws its precision. The global average temperature in 2023 was approximately 1.45 degrees Celsius above the pre-industrial baseline, the closest the planet has come to the 1.5 degree threshold that the Paris Agreement identified as a target limit. 2024 surpassed 2023 as the hottest year on record, and 2025 continued the trend into territory that was not expected to arrive until later in the century under moderate emissions scenarios. The emissions trajectory that the world is currently on, with global CO2 emissions still at near record levels despite substantial growth in renewable energy, is consistent with warming of approximately 2.5 to 3 degrees Celsius above pre-industrial levels by the end of the century under current policies. At 3 degrees of warming, the extreme heat events that are currently occurring once every 5 to 10 years in parts of the United States would occur multiple times per decade. The events that are currently occurring once per decade would occur multiple times per year. The threshold of truly unlivable heat, sustained wet bulb temperatures approaching the limits of human tolerance, would affect parts of the Gulf South and Southwest regularly enough to require fundamental rethinking of whether those regions can support large human populations without radical infrastructure adaptation. The adaptation challenge is real, and it is being addressed unevenly. Cooling centers in urban areas, publicly accessible air-conditioned spaces open during extreme heat events, are an established intervention, but their effectiveness depends on people actually getting to them, which is difficult for elderly people living alone, people without transportation, and people who do not know such resources exist. Green infrastructure. Expanding urban tree canopy, replacing impervious surfaces with permeable materials, creating parks and green spaces, is a proven intervention for reducing urban heat island intensity, but it operates on a timescale of decades and requires sustained investment and planning. Building codes that require adequate insulation and passive cooling capacity are being updated in some jurisdictions and ignored in others. Outdoor work regulations. Heat illness prevention standards that mandate rest breaks, shade, and water access for outdoor workers above certain temperature thresholds exist in California, Washington, and Oregon, and at the federal level through OSHA emergency rules, but are not uniformly enforced. The gap between what adaptation science says is necessary and what is actually being implemented at scale is substantial. Not because the solutions are unknown, but because they require sustained political will, sustained funding, and sustained coordination across jurisdictions that American governance structures make genuinely difficult. The future that the current trajectory is producing will not arrive uniformly or all at once. It will arrive incrementally, event by event, record by record. Each summer a little hotter than the last, each extreme event a little more likely than the one before it. Each baseline a little further from the one that the infrastructure and the culture were built for. The American Southwest will continue to push the boundaries of human habitation without massive cooling infrastructure. The Gulf Coast will continue to accumulate heat stress hours. The agricultural heartland will continue to face growing season stress. The urban heat islands will continue to concentrate mortality risk in the neighborhoods that already carry the greatest burden. This is not speculation. It is the projection of already observed trends through physics and documented feedback mechanisms. The question that matters is not whether these trends will continue. The physics makes that answer clear. The question that matters is how quickly and how equitably the response will scale to match the pace and the inequitable distribution of what is coming. The economic cost of extreme heat in America is being calculated with increasing precision, and the figures that emerge from serious economic analysis are large enough to reframe the political debate, or should be, if the debate were fully engaged with the available evidence. A 2023 study from the Brookings Institution estimated that heat already costs the American economy approximately $100 billion annually in lost productivity, increased healthcare expenditure, and infrastructure damage, a figure that grows substantially with each additional degree of warming. Lost labor productivity alone, the measurable decline in output per worker hour at elevated temperatures, documented across construction, agriculture, manufacturing, and outdoor services, accounts for tens of billions of dollars per year and is projected to grow to hundreds of billions annually by mid-century under moderate warming scenarios. The economic logic is straightforward. Human cognitive and physical performance degrades at sustained high temperatures. The degradation follows a well-documented dose-response relationship, and the sectors of the American economy most exposed to outdoor temperatures are also among the sectors with the thinnest profit margins and the least capacity to absorb shocks. When a construction crew in Phoenix cannot safely work between noon and 4 in the afternoon for 3 months of the year, that is not an individual inconvenience. It is a structural economic constraint on an entire industry in an entire region, one that is growing more binding with each passing decade. The agricultural economics of extreme heat deserves particular attention because the feedback mechanisms between heat stress, food prices, and social instability are global in their reach. American agricultural productivity is not just an American economic concern. It is a global food security concern, because the United States accounts for roughly 30% of global corn exports and 35% of global soybean exports, commodities that form the caloric foundation of livestock production on every inhabited continent. When heat stress reduces yields in the American Corn Belt, which peer-reviewed research consistently shows it does, at a rate of roughly 6% per degree Celsius of warming during the growing season, the price effects ripple through global commodity markets within weeks. The 2012 Midwest drought, which was not the worst heat-drought combination in terms of absolute temperature anomalies compared to more recent summers, reduced U.S. corn yields by approximately 13% and contributed to a spike in global food prices that affected food security in import-dependent countries across Africa, the Middle East, and Southeast Asia. The heat trends in the American agricultural heartland are thus not separable from the political stability of regions far removed from the American Midwest, a connection that national security analysts at the Pentagon and the CIA have been documenting for over a decade in assessments that remain substantially underreported in mainstream coverage of the heat issue. Power grid vulnerability under extreme heat is a technical problem with political dimensions that make it unusually difficult to solve within normal American governance frameworks. The fundamental issue is that peak electricity demand, driven overwhelmingly by air conditioning during heat events, has been growing faster than generating and transmission capacity in most regions of the country. The regulatory framework governing electricity markets in the United States is fragmented across federal and state jurisdictions, organized around different principles in different regions, and structured around incentives that have historically rewarded building generation capacity more than building transmission capacity or storage. When a heat dome covers multiple states simultaneously, transmission constraints between regions prevent electricity from flowing from areas with surplus to areas with deficit, even when the generation physically exists somewhere in the country. The Federal Energy Regulatory Commission has authority over interstate transmission, but building new transmission lines requires navigating a permitting process that routinely takes a decade or more and faces opposition from a combination of environmental reviews, local government objections, and utility incumbents protecting existing market positions. The result is a grid architecture that was adequate for the demand patterns and climate of the mid-20th century, and is increasingly mismatched to both the demand patterns and the climate of the early 21st century. The human physiology of heat stress is worth understanding in concrete terms, because the abstract language of temperature anomalies and degrees of warming can obscure what is actually happening inside human bodies during extreme heat events. Core body temperature in healthy adults is maintained within a narrow range, roughly 97 to 99 degrees Fahrenheit, through a combination of sweating, radiation, convection, and conduction. When ambient temperature approaches or exceeds skin temperature, the radiation and convection mechanisms become ineffective or reversed, and sweating becomes the primary cooling pathway. Sweating requires water, roughly 1 to 1.5 liters per hour of intense heat exposure, and it requires that the water vapor produced can actually diffuse away from the skin surface into the surrounding air. When relative humidity is high, this diffusion slows. When wind is absent, the water-saturated boundary layer around the skin does not refresh, and cooling efficiency drops further. Heat exhaustion, the stage before heat stroke, manifests as heavy sweating, weakness, cold and clammy skin, a fast and weak pulse, nausea, and possible fainting. Heat stroke, the medical emergency, manifests as body temperature above 104 degrees Fahrenheit, hot and red skin that may be dry or damp, a rapid and strong pulse, and possible loss of consciousness. Without rapid cooling, heat stroke kills. The physiological window between manageable heat stress and fatal heat stroke can close within minutes for vulnerable individuals, particularly the elderly who sweat less efficiently, and people on certain medications that impair thermoregulation, including some antipsychotics, antihistamines, diuretics, and beta blockers. The concept of heat-related mortality as fundamentally a social phenomenon, not merely a physiological one, is supported by a body of literature that has been building since Eric Kleinenberg's landmark sociological study of the 1995 Chicago heat wave, which killed approximately 739 people over 5 days in July of that year. Kleinenberg's finding was not that the people who died were simply unlucky or particularly physically vulnerable. It was that the people who died were disproportionately elderly, disproportionately black, and disproportionately socially isolated. Neighborhoods with high social cohesion, where neighbors checked on each other, where community organizations were active, where people had social networks that would notice an absence, had dramatically lower mortality rates than socially fragmented neighborhoods of similar demographics. The presence of a single functional social relationship, a neighbor who knocked on the door, a family member who called, appears to have been the difference between life and death for hundreds of individuals. This finding has been replicated in studies of heat events in France, Portugal, Spain, and multiple American cities. It suggests that investment in social infrastructure, community organizations, senior services, neighborhood cohesion programs, is a legitimate heat adaptation intervention with measurable mortality impact, one that is systematically undervalued in adaptation planning that focuses primarily on physical infrastructure like cooling centers and upgraded electrical grids. The science of what is driving the acceleration of extreme heat events goes beyond simply adding greenhouse gases to the atmosphere and expecting a linear warming response. Several feedback mechanisms are amplifying the rate of warming in ways that make the current decade's observations run ahead of the projections that were made in the 1990s and 2000s. The Arctic is warming roughly 4 times faster than the global average, a phenomenon called Arctic amplification. And this rapid Arctic warming is reducing the temperature gradient between the Arctic and the mid-latitudes that drives the jet stream. A weaker temperature gradient produces a more meandering, slower-moving jet stream that tends to form persistent blocking patterns, the large-scale atmospheric configurations that keep weather systems stalled over one region for weeks at a time. Heat domes are a manifestation of blocking patterns. A more meridional, slower jet stream means more frequent and more persistent blocking, which means more frequent and more persistent heat domes. The connection between Arctic warming and increased heat dome persistence is an area of active research, with some scientific disagreement about the precise mechanisms and their relative importance. But the observational correlation between reduced Arctic sea ice extent and increased mid-latitude weather persistence is robust across multiple datasets and multiple research groups. The role of ocean temperatures in American heat patterns is a dimension that receives less attention than it deserves. The record-breaking marine heat wave of 2023, during which global average sea surface temperatures reached values unprecedented in the observational record, contributed to atmospheric conditions that amplified land-based heat events across multiple regions. The Gulf of Mexico, which feeds moisture into summer weather systems across the American South, reached temperatures approaching 90 degrees Fahrenheit at the surface in the summer of 2023. Temperatures that loaded the lower atmosphere with exceptional amounts of water vapor. This elevated moisture amplifies heat indices in the southeast and Gulf Coast, exacerbating the physiological stress of heat events beyond what air temperature alone would suggest. The Pacific Ocean's influence on American heat is mediated through patterns like the Pacific Decadal Oscillation and El Niño Southern Oscillation, climate modes that shift atmospheric circulation patterns on timescales of years to decades, and can amplify or suppress heat events across different regions. The strong El Niño of 2023 and 2024 contributed to the record global temperatures of those years and is expected to leave a thermal legacy in the coupled ocean-atmosphere system that influences conditions well beyond the immediate El Niño period. The experience of extreme heat is not evenly distributed, even within individual households and within individual bodies. And this granular inequality is worth examining because it illuminates the mechanisms of harm. In a household with central air conditioning, a functioning unit, and the financial capacity to run it continuously through a heat event, extreme outdoor temperatures are primarily an inconvenience, a reason not to go outside, a reason utility bills are higher, a backdrop to news coverage of something happening to other people. In a household without air conditioning, or with a window unit that struggles against an outdoor temperature of 110 degrees Fahrenheit in an apartment with poor insulation and low ventilation on the upper floor of a building that has absorbed a full day of solar radiation, the same outdoor temperature is a physiological emergency that develops gradually over hours and days. The cumulative thermal load in such a space does not follow outdoor temperatures downward when the sun sets, because thermal mass in the building releases stored heat overnight, often keeping interior temperatures above outdoor temperatures through much of the night. This is the mechanism by which multi-day heat events kill, not the peak daytime temperature, which the body can survive for hours, but the inability to recover overnight, combined with the cumulative physiological burden of multiple consecutive days of heat stress. The duration of heat events matters at least as much as the peak intensity. And duration is one of the dimensions along which American summer heat is increasing most clearly in the observational record. The children who are growing up in the American Southwest and Gulf South today are doing so in a climate that is measurably and substantially different from the one in which their parents grew up. Not in some abstract global sense, but in concrete terms that affect school schedules, outdoor recess policies, youth sports practices and games, and the basic freedom to play outside during daylight hours without medical risk. School districts in Phoenix, Tucson, Las Vegas, and multiple Texas cities have modified or eliminated outdoor recess during portions of the school year due to heat. Youth soccer and football leagues in parts of the Southwest have moved practices to early morning or eliminated them entirely during summer months. The outdoor summer experience that has been culturally central to American childhood for generations, the freedom to be outside, to run, to sweat, to play in the neighborhood until the streetlights come on, is being compressed and in some cases eliminated by ambient conditions that make prolonged outdoor exposure genuinely dangerous for young bodies whose thermoregulatory systems are less efficient than healthy adults. This is not a dramatic single-point crisis. It is a gradual, cumulative narrowing of lived experience that is already observable and will deepen with each successive decade of continued warming. The political economy of addressing heat at the scale required is genuinely difficult in ways that go beyond the familiar polarization around climate change. Unlike flooding, which produces dramatic imagery, specific geographic losers, and politically mobilizing property damage, extreme heat kills people in ways that are relatively invisible. Individually, in their homes, in ways that get attributed to heart attacks and kidney failure rather than to temperature. Unlike hurricanes, which produce the kind of acute, concentrated destruction that generates immediate political response, heat waves produce diffuse, distributed mortality that does not generate the same political and media intensity. Unlike wildfire, which produces spectacular visuals and destroys property whose loss is immediately and concretely felt, heat stress produces physiological degradation that is gradual enough to be normalized. The invisibility of heat mortality is a genuine political problem for mobilizing the investment and policy change that adaptation requires. Cities and states that have made serious progress on heat adaptation: Los Angeles, which has appointed a chief heat officer; Phoenix, which has made significant investments in cooling infrastructure; Miami-Dade County, which has implemented a comprehensive heat action plan, have done so largely through the efforts of specific individuals within government who understood the issue deeply and found ways to make the invisible visible through data, storytelling, and sustained advocacy. The specific trajectory of American heat through the next several decades, under different emission scenarios, produces numbers that are instructive precisely because they are concrete rather than abstract. Under a scenario in which global emissions peak within the next few years and decline rapidly, roughly corresponding to the International Energy Agency's net zero by 2050 scenario, Phoenix would experience roughly 45 days per year above 110 degrees Fahrenheit by mid-century, compared to roughly 18 days per year in the current baseline. Under a scenario corresponding to current policies without significant additional action, roughly 2.5 to 3 degrees of global warming by late century, Phoenix would experience approximately 120 days per year above 110 degrees Fahrenheit by mid-century. The difference between those two numbers, 45 days versus 120 days, is not merely a technical climate projection. It is the difference between a challenging but manageable climate that can be adapted to with substantial investment and a fundamentally different thermal environment that would require reconsideration of the viability of large-scale permanent human habitation in one of the fastest-growing metropolitan areas in the United States. These projections come from peer-reviewed research using standard climate model ensembles and are not the extreme end of the projection range. They are central estimates. The international context matters for understanding American heat in a way that is often missing from domestic coverage. The United States is not experiencing an isolated heat crisis. It is experiencing one manifestation of a global thermal transformation that is simultaneously producing unprecedented heat in India, Pakistan, Southern Europe, Sub-Saharan Africa, and the Middle East. In some of these regions, the convergence of extreme heat with poverty, limited cooling infrastructure, outdoor agricultural labor dependence, and conflict creates conditions of acute human suffering on a scale that dwarfs what is being experienced in the United States. Pakistan's heat wave of 2022, which occurred simultaneously with catastrophic flooding driven by the same climate dynamics, caused acute suffering for tens of millions of people and directly preceded economic and political instability that had global consequences. India's agricultural regions experience heat stress events that threaten food production for a population of 1.4 billion people. The humanitarian implications of global heat are not separable from American interests through the mechanisms of refugee flows, food price instability, geopolitical conflict, and pandemic risk that are amplified by climate stress. Understanding American heat as a domestic issue in isolation from its global context produces an incomplete picture of both the causes and the appropriate scale of response. The scientific community studying extreme heat has reached a level of certainty about the basic direction and approximate magnitude of future warming that is rarely communicated clearly to the public. Not because scientists are reluctant to speak plainly, but because the communication infrastructure between scientific assessment and public understanding has persistent gaps that are exploited by those with interests in maintaining uncertainty. The Intergovernmental Panel on Climate Change Sixth Assessment Report, published between 2021 and 2023, represents the synthesis of thousands of peer-reviewed studies by hundreds of scientists across dozens of countries. Its conclusions about the direction of warming, the role of human activities in driving it, and the consequences of continued emissions are stated with levels of confidence that, in scientific language, mean the evidence is overwhelming and the conclusions are not seriously contested within the relevant expert communities. The uncertainty that exists is not about whether warming will continue, it will, or whether extreme heat events will become more frequent and more intense, they will, but about the precise rate and regional distribution of changes that depend on the trajectory of future emissions, which is determined by human decisions that have not yet been made. The phrase "only the beginning" in this context is not alarmism. It is a straightforward characterization of what the physics produces when the known forcings are projected forward through time. The mental health dimensions of extreme heat are among the most under-examined aspects of the crisis, and the research that has accumulated over the past decade paints a picture that is considerably more alarming than the public conversation around heat typically acknowledges. The connection between high ambient temperatures and psychological distress is not a new observation. It has been documented in criminological literature through the heat aggression hypothesis since the 1980s, and in psychiatric literature through the seasonal patterns of certain mood disorders for longer. What is newer is the systematic epidemiological documentation of the relationship between heat and mental health outcomes at the population level. A comprehensive analysis published in Nature Climate Change in 2018, covering over 2 million respondents in the United States and Mexico, found that a single month with an average temperature 1 degree Celsius above normal increased the probability of mental health difficulties by approximately 2%. A small per capita effect that aggregates to millions of additional cases of psychological distress across large populations during hot summers. The mechanisms proposed include direct physiological effects of heat on serotonin and dopamine systems, sleep disruption caused by elevated overnight temperatures, reducing the restorative function of sleep, social isolation driven by people staying indoors during extreme heat events, and economic stress from heat-related job losses, agricultural failures, and elevated cooling costs. All of these mechanisms are biologically or socially plausible, and several have supporting experimental evidence. The aggregate mental health burden of a substantially hotter America is a cost that is not currently reflected in most economic assessments of climate change impacts. Suicide rates and heat temperature follow a relationship that has been documented across multiple countries and multiple decades, and the relationship is robust enough to be considered well established in the epidemiological literature. A 2019 study in Nature Climate Change, analyzing data from both the United States and Mexico, found that a 1 degree Celsius increase in monthly average temperature was associated with approximately 1% increase in suicide rates in the United States and approximately 2% in Mexico. Effects that, when projected forward under moderate warming scenarios, translate to tens of thousands of additional suicides annually across the two countries by mid-century. The biological mechanism most commonly proposed involves the role of serotonin in thermoregulation, the same neurotransmitter system implicated in mood regulation, and the hypothesis that heat-induced dysregulation of serotonin signaling creates conditions of increased impulsivity and reduced emotional regulation that raise suicide risk. This is a biologically plausible mechanism supported by some experimental evidence, though the precise causal chain remains an area of active research rather than settled science. What is established is the population-level statistical association, which is large enough and consistent enough across independent datasets to be policy relevant regardless of the precise mechanistic explanation. The legal and regulatory landscape governing heat protection for workers in the United States is a patchwork that reflects decades of insufficient federal action and uneven state-level response. The Occupational Safety and Health Administration has authority to regulate workplace hazards, and heat illness is a documented and preventable workplace hazard. Heat kills more workers in the United States each year than any other weather-related cause, with the agricultural sector bearing the highest burden, followed by construction. Despite this, OSHA did not have a comprehensive federal heat standard as of the time of writing, instead relying on a general duty clause that requires employers to provide a safe workplace, which has proven inadequate to protect outdoor workers in practice. The agency proposed a federal heat standard in 2021, but the rulemaking process is slow, and the standard had not been finalized through multiple regulatory cycles. California, Washington, Oregon, Colorado, and Minnesota have implemented state-level heat standards for outdoor workers, requiring water, rest breaks in shade, and acclimatization protocols during periods of elevated heat. The states without such standards, which include most of the South and much of the agricultural Midwest, provide substantially less legal protection to the workers who face the highest heat exposure. The result is a system in which the legal protection a worker receives from heat illness depends substantially on which state they happen to be employed in, a geographic lottery in which the hottest states are often the least protective. The innovation landscape around heat adaptation is more active than most public discussions of the problem suggest, and some of the technologies and approaches being developed or deployed at scale have genuine potential to reduce harm if they can be implemented at the necessary speed and breadth. Radiative cooling materials. Surfaces engineered to reflect solar radiation in the visible spectrum while simultaneously emitting thermal radiation in the mid-infrared band, thereby losing heat even in direct sunlight, have been demonstrated in laboratory and field settings to cool surfaces by 5 to 15 degrees Celsius below ambient air temperature without any energy input. Commercial products based on this principle are entering the market, and their application to roofing materials, road surfaces, and urban infrastructure has the potential to measurably reduce urban heat island intensity in the cities that deploy them at scale. Phase change materials, substances that absorb large amounts of heat as they melt and release it as they solidify, buffering temperature swings, are being incorporated into building materials to reduce the thermal load on buildings during peak heat hours, reducing both indoor temperatures and air conditioning energy demand. Personal cooling technologies. Lightweight wearable cooling devices using evaporative or thermoelectric principles are being developed for outdoor workers as a supplement to administrative controls like rest breaks and shade. None of these technologies is a substitute for reducing the emissions that are driving the warming, but they represent a realistic toolkit for reducing harm in the decades during which the accumulated warming in the climate system will continue to manifest regardless of emissions trajectory. The tree canopy dimension of urban heat is one of the most thoroughly documented and most neglected elements of the adaptation conversation. Trees reduce urban temperatures through two mechanisms. They shade surfaces, preventing solar radiation from being absorbed and re-emitted as heat, and they transpire water vapor, which cools the surrounding air through the same evaporative process that makes sweating effective. Studies consistently show that a mature urban tree can cool the surrounding air by approximately 2 to 8 degrees Fahrenheit through combined shading and transpiration effects. The challenge is that urban tree canopy is unequally distributed in almost every American city. Wealthier and whiter neighborhoods have substantially more tree cover than lower income and higher minority population neighborhoods, a disparity that has been systematically documented across hundreds of American cities using satellite remote sensing data. This disparity is both a legacy of historical investment patterns and a product of ongoing maintenance differentials. Trees in lower-income neighborhoods are more likely to die from lack of maintenance, drought stress, or pests, and less likely to be replaced. Several American cities, Los Angeles, Houston, Atlanta, and others have launched tree equity programs aimed at specifically targeting canopy expansion in heat-vulnerable, low-canopy neighborhoods. These programs are meaningful interventions, but they operate on timescales of decades. A tree planted today will not provide significant cooling until it is mature, and require sustained funding through multiple budget cycles and multiple administrations to realize their intended benefits. The insurance industry's response to extreme heat is a leading indicator of how the private sector is pricing the risks that governments have been slow to address. Property insurance companies have been withdrawing from markets in California and Florida, primarily in response to wildfire and hurricane risk, respectively. But the actuarial models underlying these decisions also incorporate heat-related risks to property values and to the economic viability of the regions involved. When insurers leave a market, property owners either go uninsured, accepting risk that most cannot absorb, or fall back on state-run insurers of last resort that are undercapitalized relative to the risks they carry. The withdrawal of private insurance from high-risk climate zones is creating what economists call a market signal about the long-term habitability of certain regions. A signal that is beginning to affect property values, mortgage availability, and population migration patterns. Research published by the First Street Foundation has documented that flood and fire risk are already producing measurable depressions in property values in affected areas, and that the markets are only partially pricing the risks because significant portions of climate risk are not yet fully visible to buyers. As heat risk becomes better modeled and better communicated, its impact on property markets in the most affected regions is likely to grow, creating economic pressure for adaptation that political systems have so far been unable to generate through regulatory channels alone. The migration patterns that extreme heat is already driving are visible in population data from the most affected American regions, though disentangling heat from other drivers of migration, economic opportunity, housing cost, demographic change, is methodologically challenging. Research from Columbia University's Climate School has documented statistically significant relationships between extreme heat exposure and outmigration from counties in the American South and Southwest. Controlling for economic factors, the correlation between heat stress intensity and population outflow is real and growing. The destinations of people leaving the hottest counties tend to be higher latitude and higher elevation locations, suggesting that at least some migration is driven by a search for cooler conditions. Mountain West cities, Boise, Spokane, Salt Lake City, Bozeman, have been among the fastest growing American metropolitan areas in the past decade, receiving in-migration from both coastal cities and from hotter Sunbelt locations. This migration is producing its own pressures on receiving communities: housing costs, infrastructure strain, water resource competition in places like the Mountain West that are themselves facing intensifying drought, creating second-order consequences of heat-driven population movement that are only beginning to be studied systematically. The comparative international experience of heat adaptation provides instructive examples of what is possible when governments treat extreme heat as the public health emergency it is, rather than as a natural phenomenon to be weathered individually. Japan has perhaps the most comprehensive national heat illness prevention system of any country, including a nationally coordinated alert system, mandatory cooling shelters open to the public, regular welfare checks on elderly residents, and workplace heat standards enforced through routine inspection. France, after the catastrophic 2003 heat wave that killed approximately 15,000 people, an event that concentrated public and political attention on heat as a systemic failure rather than a natural disaster, implemented a national heatwave plan that has measurably reduced mortality in subsequent heat events, including events that were physically as intense as 2003. The key elements of the French plan are not technologically sophisticated. They include a national alert system with clear thresholds, municipal plans identifying vulnerable individuals and ensuring contact, funding for community health workers to make direct welfare checks, and public communication that treats heat as a medical emergency requiring active response. American cities that have implemented similar elements, Los Angeles, Phoenix, Miami-Dade, have documented reductions in heat-related emergency room visits and hospitalizations relative to comparable cities without such plans. The evidence that organized public health responses to extreme heat save lives is substantial. The barrier to implementation is not knowledge. It is political prioritization and sustained funding. The thermal transformation of American sports culture is a small but revealing dimension of how pervasively rising heat is reshaping daily life. The National Football League, which traditionally begins its preseason training camps in late July and August, historically the hottest period of the American summer, has been forced to substantially modify practice protocols across its teams. Heat acclimatization guidelines now limit full contact practice in pads during the first 2 weeks of training camp, require rest periods in air-conditioned facilities during practice days, and mandate wet bulb globe temperature monitoring throughout outdoor sessions. Major League Baseball has seen increasing numbers of games delayed or shortened due to extreme heat conditions across its Sunbelt franchises. The United States Tennis Association modified scheduling at the U.S. Open in Flushing Meadows, New York, a tournament that historically occurred in late August and early September when New York heat can be extreme, in response to heat-related player illness. High school athletics programs across the South and Southwest have experienced multiple heat-related deaths of student athletes during practices and games, generating legal liability for school districts and driving mandatory policy changes at the state level. The physical culture of American competitive sports, built over more than a century around the assumption that summer heat is an endurance challenge to be overcome, not a medical constraint to be respected, is being forced to adapt its assumptions to a thermal environment that is fundamentally different from the one in which its traditions were established. The question of what American cities will actually look like physically if the adaptation challenge is met seriously, not merely rhetorically but in terms of infrastructure, land use, and built environment, is worth considering as a concrete exercise in imagination rooted in current technical knowledge. A heat-adapted American city in the mid-century climate would have substantially more tree canopy than current cities, distributed equitably across income and demographic groups through sustained public investment. Its streets would have more shade structures, more reflective pavements, more frequent misting stations in pedestrian areas during heat events. Its building stock would have higher insulation standards, better passive ventilation, and more distributed cooling capacity, including smaller, more efficient air conditioning units that can be powered by rooftop solar even during grid stress events. Its electrical grid would have more storage capacity, both utility scale and distributed, reducing dependence on consistent generation during peak demand periods. Its water system would have greater storage and efficiency capacity to support vegetation during drought periods. Its emergency management system would have a continuously updated registry of heat-vulnerable residents and a reliable mechanism for making direct contact with those residents during heat events. Its outdoor work regulations would have enforceable heat standards with real inspection capacity. None of these elements requires technology that does not currently exist. All of them require sustained investment and political will over multiple decades. The gap between the city described above and most American cities today is the gap between the adaptation challenge that has been identified and the adaptation response that has so far been mobilized. The pace of change in the American heat pattern is itself one of the most striking features of the current situation, because it has consistently outrun the projections that were considered most likely at the time they were made. The global average temperature in 2023 exceeded the projections of the IPCC's fifth assessment report, published in 2013, for that year under moderate to high emissions scenarios. The frequency of extreme heat events in the American Southwest has increased faster than the central projections of climate models for several reasons that are now reasonably well understood. Models historically underestimated the rate of Arctic warming and its effects on jet stream persistence. Models underestimated the feedback between soil moisture deficit and surface temperature amplification. And models underestimated the contribution of rapid reductions in aerosol pollution, which has a cooling effect, that occurred as emissions regulations reduced particulate pollution from coal plants and heavy industry. Each of these factors has pushed observed warming ahead of modeled projections. The implication for interpreting future projections is not that the models are simply wrong. They have been validated against many aspects of observed climate change with impressive accuracy, but that the central projections should be understood as minimum estimates for planning purposes in the most sensitive and vulnerable sectors, with the upper range of projections representing the scenarios that responsible risk management requires preparing for. The generation of Americans who will be in their 20s and 30s at mid-century are the ones who will live most of their adult lives in the climate that current emissions trajectories are producing, and the heat they will experience as middle-aged adults in 2060 or 2070 is being determined in significant part by decisions being made right now about energy systems, urban planning, agricultural practice, and international climate policy. This is not a rhetorical point about intergenerational equity, though it is that. It is a concrete statement about the causal chain connecting present emissions to future temperature, mediated by the physics of carbon dioxide persistence in the atmosphere and the thermal inertia of the ocean system. Carbon dioxide emitted today will remain in the atmosphere for centuries. The warming commitment already locked in by accumulated historical emissions, warming that will occur even if all emissions stop tomorrow, is estimated at approximately an additional 0.2 to 0.5 of a degree Celsius above current temperatures. The warming from emissions that continue to occur during the decades it takes to complete an energy transition will add to that committed warming. The heat pattern that is taking over America is not a crisis that will resolve itself when attention moves on or when a particular political cycle ends. It is a decades-long transformation, whose trajectory is determined by the physics of a system with very long memory, and whose impacts on human lives are only beginning to be fully experienced across the communities, industries, and ecosystems that constitute the American landscape. The relationship between nighttime heat and sleep deprivation is one of the most direct mechanisms through which rising temperatures degrade human functioning, and the public health implications of this relationship are substantially larger than is generally appreciated. Sleep is not merely rest. It is the period during which the brain consolidates memory, clears metabolic waste products through the glymphatic system, regulates hormone levels, including cortisol and insulin, repairs cellular damage, and restores cognitive and emotional regulatory capacity. All of these functions are temperature dependent. The brain's transition into deep, slow-wave sleep requires a drop in core body temperature, and this drop becomes more difficult to achieve when ambient temperatures remain elevated through the night. A landmark study published in the journal One Earth in 2022, analyzing sleep data from nearly 70,000 individuals across 68 countries using wrist accelerometers, found that on nights when outdoor temperatures exceeded 77 degrees Fahrenheit, people slept approximately 14 minutes less per night, an effect that was substantially larger for elderly individuals, residents of lower-income countries with less access to cooling, and women. The cumulative sleep deficit across a summer with multiple hot nights translates into measurable cognitive impairment, elevated accident risk, reduced immune function, and increased chronic disease risk. When projected forward against the expected increase in hot nights under continued warming, the number of nights above 77 degrees Fahrenheit in cities across the American South is already roughly double what it was in the 1980s, and is projected to double again by mid-century. The aggregate sleep deprivation burden on the American population becomes a substantial public health problem that has received very little policy attention relative to its magnitude. The economics of cooling are fundamentally regressive in a way that compounds the health inequity already described. Air conditioning electricity costs represent a larger fraction of household income for lower-income families than for wealthier ones, because lower-income households live in less energy-efficient housing stock that requires more electricity to cool to the same temperature, and because the monthly energy burden as a percentage of income is inherently larger for smaller incomes. The Low-Income Home Energy Assistance Program, the primary federal program providing heating and cooling assistance to low-income households, has been chronically underfunded relative to need, in recent years serving roughly 1 in 6 eligible households. State-level weatherization programs that could reduce the energy burden by improving insulation and sealing air leaks have long waiting lists in most states. The result is a system in which low-income households face the worst heat exposure, in the least efficient housing, at the highest proportional cost, with the least access to assistance. A triple compounding of disadvantage that is documented in utility disconnection data, in heat illness hospitalizations, and in summer mortality statistics. Utility disconnection during summer months, which cuts off air conditioning service to households that cannot pay their bills, has been linked to heat-related mortality in multiple studies. Several states prohibit utility disconnection during winter months for heating safety reasons, but impose no analogous summer restrictions for cooling, reflecting a historical assumption that heat is less life-threatening than cold, that the current climate has rendered medically inaccurate in large portions of the country. The specific experience of working outside in extreme heat is something that most people who work indoors have not experienced in a way that allows them to fully comprehend what is being asked of agricultural workers, construction crews, and other outdoor laborers as American summers intensify. In 105-degree Fahrenheit heat with moderate humidity, conditions that are now routine in parts of Texas, Arizona, and the Central Valley of California during summer months, a worker performing moderate physical labor generates substantial metabolic heat on top of the ambient thermal load. The body's cooling system responds by increasing sweat rate, directing blood flow to the skin surface for radiation, and elevating heart rate to maintain circulation. After 2 to 3 hours in these conditions, without adequate shade, rest, and hydration, core body temperature begins to rise. The first symptoms, fatigue, headache, nausea, are easy to dismiss or to push through when the economic pressure to complete a job is real and immediate. The second stage, confusion, slurred speech, coordination loss, comes on fast enough that a worker may not be able to self-assess that they have crossed into medical emergency territory. By the time heat stroke is clinically apparent, the window for preventing serious organ damage or death is measured in minutes, not hours. Heat stroke deaths of outdoor workers in the United States are distributed across agricultural and construction sectors, are substantially undercounted in official statistics because of misclassification of heat as a contributing rather than primary cause, and are disproportionately concentrated among Latino workers, who account for roughly 73% of agricultural workers nationally and face a combination of heat exposure, labor exploitation, and barriers to accessing medical care that creates acute vulnerability. The cooling center model as a public health intervention deserves both credit for what it accomplishes and honest analysis of its limitations. Cooling centers, designated air-conditioned spaces, often libraries, community centers, or government buildings, that are made accessible to the public during heat events, can genuinely save lives by providing a refuge for people who would otherwise remain in dangerously hot environments. Several studies have documented that cities with well-publicized cooling center networks have lower heat-related mortality during extreme events than comparable cities without them. The limitations are real, however, and not adequately discussed in most public health communication about heat. Cooling centers require people to travel to them, which means they are most accessible to people who can physically get there, have transportation, know they exist, and feel safe and welcome in public institutional spaces. Elderly people who live alone and have mobility limitations may not be able to reach a cooling center even when one is a few blocks away. People experiencing homelessness face barriers of stigma and institutional mistrust that reduce uptake. People without access to transportation in car-dependent suburban and rural environments cannot reach centers that are located in downtown or commercial areas served by public transit. The most effective supplement to cooling centers: direct outreach to identified vulnerable individuals, including welfare checks by community health workers, neighbors, or emergency services, requires investment in community infrastructure that most American cities have not made at the scale the need requires. Cooling centers are necessary but not sufficient, and their limitations fall most heavily on the people who are already most at risk. The water security dimension of extreme heat is a compounding problem that is particularly acute in the American West and is beginning to affect parts of the South and Midwest that historically had more reliable water supplies. The relationship between heat and water is bidirectional in several important ways. Extreme heat increases evaporation from reservoirs and soil, reducing effective water supply. It increases agricultural irrigation demand, drawing more heavily on aquifers and surface water supplies that are already stressed. It increases urban water demand for cooling, landscaping, and personal consumption. At the same time, the warming-driven changes in precipitation patterns that accompany temperature increases are reducing snowpack in the mountain ranges that serve as natural water storage across the West. The Sierra Nevada, the Rockies, the Cascades, shifting runoff earlier in the year and reducing the summer availability of water precisely when summer heat is driving demand to its annual peak. The Ogallala Aquifer, which underlies roughly 170,000 square miles of the High Plains and supports irrigation for approximately 30% of all American groundwater irrigated cropland, is being drawn down at rates that substantially exceed natural recharge, a depletion that is accelerating as heat increases crop water demand. Several modeling studies project regional aquifer depletion scenarios that would eliminate irrigation capacity in parts of the High Plains within decades under continued extraction at current rates, with consequences for agricultural productivity that would be felt globally through commodity markets. The emergency medical system in heat-affected American cities is experiencing a strain during extreme heat events that has not been fully communicated to the public. Emergency room visits for heat-related illness spike dramatically during heat waves, doubling, tripling, or more compared to baseline visit rates during peak events, at precisely the times when emergency departments are also experiencing elevated volumes of cardiovascular emergencies, respiratory emergencies, and other heat-exacerbated conditions. Emergency medical services, ambulances, face a combinatorial demand surge that can compromise response times across the entire call volume, not just for heat-related calls. Several emergency management analyses following major heat events have documented response time degradation across metropolitan areas during peak heat, increasing mortality risk for calls of all types. Hospital capacity becomes constrained during prolonged heat events as patients requiring cooling, fluid replacement, and observation occupy beds at above baseline rates. The medical system's capacity to absorb heat-driven demand surges is not elastic at short notice. It is constrained by physical bed capacity, staffing, and pharmaceutical supplies that cannot be rapidly scaled. This is a known vulnerability that has been documented in after-action reviews following major heat events and has generally not resulted in the sustained capacity investments that would address it before the next event arrives. The role of social media and digital communication in both exacerbating and mitigating heat risk is complex and largely understudied. On the mitigation side, real-time heat alert systems that push notifications to smartphones, social media coordination of cooling resource information, and digital wellness check networks that allow community members to flag vulnerable neighbors have all demonstrated value in reducing harm during specific events. The rapid spread of information about cooling center locations, extended library hours, and heat illness warning signs through social platforms during heat events has genuinely helped people access resources they would not otherwise have found. On the risk amplification side, several documented patterns are concerning. Social media consumption, particularly passive scrolling, tends to occur in climate-controlled environments, but simultaneously reduces social engagement with physical neighbors, potentially contributing to the social isolation that is itself a major heat mortality risk factor. Misinformation about heat illness, including conspiracy claims about heat alerts being fabricated or exaggerated for political purposes, circulates rapidly on unmoderated platforms and has been documented to suppress protective behavior in some communities during heat events. The net effect of digital media on heat adaptation is probably positive on balance, but the specific mechanisms of harm deserve more systematic study than they have received. The architectural history of American buildings is embedded in the thermal conditions of the periods during which they were constructed, and that history now constitutes a liability across large portions of the housing stock. Buildings constructed before the widespread adoption of air conditioning, which began in residential settings in the 1950s and accelerated through the 60s and 70s, were often designed with passive cooling features that have since been removed or superseded. Deep roof overhangs that shaded walls and windows, high ceilings that allowed hot air to rise away from occupied zones, cross-ventilation layouts that captured prevailing breezes, sleeping porches that allowed residents to move outdoors at night. The mass adoption of mechanical cooling systems made these passive features seem unnecessary, and they were systematically eliminated in subsequent residential construction to reduce costs. The result is a large portion of American housing stock, particularly in the South and Southwest, where passive cooling was historically most important, that lacks both adequate passive cooling capacity and adequate insulation, creating buildings that heat up rapidly, retain heat poorly, and depend entirely on mechanical cooling for habitability during extreme events. Retrofitting this housing stock to perform adequately in the climate that is arriving, adding insulation, upgrading windows, improving ventilation, and replacing inefficient older air conditioning units is a multi-trillion-dollar challenge that is nowhere near adequately funded in current building renovation programs. The feedback between extreme heat and air quality is a relationship that is particularly consequential for respiratory health and is expected to worsen significantly under continued warming. Ground-level ozone, the primary constituent of urban smog, forms through photochemical reactions involving nitrogen oxides and volatile organic compounds in the presence of sunlight and heat. Higher temperatures accelerate the chemical reactions that produce ozone, meaning that the same precursor emissions produce higher ozone concentrations on hotter days. Ozone damages lung tissue, exacerbates asthma and chronic obstructive pulmonary disease, reduces lung function, and is associated with increased mortality at high concentrations. The same periods of extreme heat that create direct heat stress are thus also periods of elevated ozone exposure, a compounding of health hazards that affects the same people who are most vulnerable to both: the elderly, people with pre-existing respiratory conditions, children whose lungs are still developing, and outdoor workers. Climate models project that ozone levels across most American cities will increase under continued warming, even if precursor emissions remain constant, meaning that air quality regulations that are adequate to protect health in the current climate will become inadequate in the future climate without additional tightening of emission limits. The ozone-heat interaction is documented in peer-reviewed literature and incorporated into EPA air quality planning, but the communication to the public of the simultaneous nature of these risks during extreme events is generally incomplete. The specific thermal experience of American prisons and jails deserves attention that it has rarely received in mainstream heat coverage, because it represents one of the most acute and least discussed intersections of heat and human rights in the country. The United States incarcerates approximately 2 million people, more per capita than any other nation, in facilities that across the South and much of the rest of the country lack air conditioning in cell blocks. Texas, the state with the largest prison population, has historically had air conditioning in only a fraction of its correctional facilities, with temperatures inside cells documented during summer heat waves at levels that would be considered occupationally hazardous for outdoor workers. Heat-related deaths in Texas prisons have been documented by advocacy groups and journalists over multiple decades, with the number attributed to heat substantially higher than official counts acknowledge. Lawsuits arguing that incarceration in extreme heat without adequate cooling constitutes cruel and unusual punishment under the Eighth Amendment have produced mixed results in federal courts. The political constituency for prison heat mitigation is limited by the marginalization of incarcerated people from political voice, and the economic constituency, prison operators, has obvious financial interests in minimizing infrastructure investment. This represents a documented, ongoing, and largely preventable harm to a population with no ability to seek relief through self-protective behavior, occurring at scale across one of the hottest regions of the country. Extreme heat's effect on the natural ecosystems of the American landscape is a dimension that receives coverage primarily through wildfire, but extends substantially beyond it to include coral reef bleaching, forest die-off, species range shifts, and phenological disruption that cascades through food webs in ways that are difficult to fully predict. The American Southwest is experiencing a ponderosa pine die-off, driven by bark beetle outbreaks that are enabled by warming temperatures. Beetle populations that were historically limited by cold winters and summer droughts are now able to reproduce more rapidly and survive more winters, overwhelming the defenses of trees that are already stressed by drought. The result is standing dead forest across millions of acres, forest that becomes fuel for increasingly intense wildfires that release stored carbon and create locally altered thermal environments that may prevent the reestablishment of forest. The transition from forest to shrubland or grassland in parts of the Southwest represents a permanent change in the ecological character of the landscape, not merely a temporary disturbance. Similarly, the timing of biological events, flowering, insect emergence, bird migration, amphibian breeding, is being disrupted by warming in ways that create mismatches between the timing of food availability and the timing of the species that depend on that food. These phenological mismatches are documented across multiple taxa and multiple American ecosystems, and their consequences for biodiversity and ecosystem function are expected to accumulate over time in ways that remain incompletely modeled. The specific contribution of urban planning decisions made over the past several decades to current heat vulnerability is a story about how infrastructure choices compound over time in ways that are difficult to reverse. The American pattern of suburban expansion, low-density, car-dependent development on the urban periphery, created communities with high impervious surface coverage, minimal tree canopy, no viable walking infrastructure, and near total dependence on personal vehicles and mechanical cooling for basic functioning. These communities were built in a climate that they were not designed for, using a development pattern that amplifies heat relative to what denser, more vegetated urban forms would produce, in locations that are now experiencing the fastest warming summer conditions in the country. The Sunbelt metropolitan expansion of the past 50 years, Phoenix growing from roughly 500,000 people in 1970 to approximately 5 million today, Las Vegas growing from roughly 300,000 to over 2 million, the Houston metropolitan area approaching 8 million, concentrated tens of millions of people in the region most exposed to extreme heat, in a development pattern that maximizes heat island intensity at precisely the historical moment when the thermal conditions of the region were beginning to transform. The accumulated infrastructure investment of that expansion, roads, pipes, buildings, power lines, cannot be quickly or cheaply reconfigured. The planning decisions of past decades have created a thermal vulnerability that will persist for generations, regardless of what adaptation investments are now made. The specific ways that heat reshapes American culture from the inside out, not merely through deaths and infrastructure failures, but through the slow renegotiation of what daily life looks and feels like, are worth examining with the same seriousness that is applied to the economic and physiological dimensions. Cultures are shaped by the climate they emerge from. The agricultural South's food traditions, the slow outdoor cooking, the porch sitting through long summer evenings, the rhythms of life organized around the relative coolness of early morning and late evening, developed in a climate where summer heat was a serious but manageable feature of the landscape. The Southwest's outdoor recreation culture, hiking, mountain biking, river recreation in the canyons, was built around the assumption that mornings were cool enough for sustained physical exertion even in July. The outdoor festival culture that became central to American entertainment from the 1960s onward, outdoor music, state fairs, county fairs, farmers markets, arts festivals, has historically assumed that summer outdoor gatherings are hot but feasible. Each of these cultural assumptions is being tested by temperatures that exceed what the activities they support were designed around, and the cultural adaptations, the retreat indoors, the shift to early morning and evening hours, the cancellation of outdoor events, are already visible to anyone paying attention. Culture changes slowly and incompletely, which is why people continue to attempt outdoor activities in conditions that are now medically inadvisable, a form of cultural lag that costs lives during the most extreme events. The phenomenon of heat migration, the movement of plant and animal species toward higher latitudes and elevations as their thermal habitats shift, is producing visible changes in the American landscape that are being documented by ecologists and increasingly observed by ordinary people paying attention to the world around them. Armadillos, once confined to Texas and the Gulf Coast, have been documented in Illinois and Indiana. Fire ants, historically limited by cold winters to the Deep South, have established populations in North Carolina and Tennessee. Kudzu, the aggressively invasive vine long associated with the American Southeast, is advancing northward into Pennsylvania and New York. Tropical fish species are appearing in waters off North Carolina, where they were historically never recorded. These are not isolated curiosities. They are systematic signals of a biological reorganization driven by shifting thermal envelopes across the continent. A reorganization that ecologists describe as a poleward migration of the tropics, with subtropical species replacing temperate ones across a zone that is advancing northward at roughly 1 kilometer per year on average, with substantial variation across different taxa and different habitat types. The consequences for American agriculture are direct and serious. Pest species that were historically controlled by cold winters are expanding their range northward into regions where crops were previously not exposed to them. The consequences for native ecosystems are harder to summarize, but are expected to involve cascading disruptions as the thermal basis of ecological communities changes faster than evolutionary adaptation can track. The intersection of extreme heat with the American housing crisis is a dimension that has received almost no systematic attention, despite its direct relevance to both problems. The shortage of affordable housing in most American metropolitan areas has produced a situation in which lower-income households are effectively pushed into the least desirable housing: older, less efficient, less well-located. Precisely the housing stock that performs worst in extreme heat. Manufactured housing, which houses approximately 17 million Americans and is disproportionately occupied by low-income households, the elderly, and rural residents, typically has thinner walls, less insulation, and more limited cooling capacity than site-built housing, making it significantly more dangerous during heat events. The spatial consequences of housing unaffordability, pushing lower-income residents into less expensive but hotter, less tree-covered, more heat island-intensive locations, are documented in the academic literature on urban heat equity. The practical implication is that the housing crisis and the heat crisis are the same crisis for a substantial portion of the population most exposed to heat-related mortality risk. Addressing one without addressing the other produces incomplete solutions. Providing cooling assistance to households that cannot afford to live in safe, efficient housing near their jobs provides temporary relief without resolving the structural vulnerability. The data infrastructure for understanding extreme heat in America is significantly better than it was a decade ago, but it remains inadequate for the scale of the problem. NOAA operates an extensive network of weather stations that measure temperature, humidity, and related variables. But the spatial resolution of this network is insufficient to capture the fine-grained urban heat island variations that determine actual human exposure in cities. The difference between conditions at an airport weather station on the urban periphery, which is what most official temperature records represent, and conditions in a dense urban neighborhood several kilometers away can be several degrees Fahrenheit, with the airport consistently recording lower temperatures than the more densely developed areas where most people actually live and work. Community science approaches, deploying large numbers of inexpensive sensors across urban areas to create high-resolution maps of urban thermal environments, have been implemented in several cities through programs like NIHHIS and COCORAS, producing data that reveals the heat island structure in far more detail than the official station network. This data is valuable for identifying the specific locations and populations most exposed to heat, enabling more targeted interventions. Expanding these networks to cover more cities and integrating the resulting data into public health planning and emergency management systems represents a relatively low-cost infrastructure investment with potentially significant returns in reduced mortality through better targeted protective responses during extreme events. The role of the military and national security establishment in both understanding and communicating heat risk is important and somewhat underappreciated in public discourse. The Department of Defense published its first climate risk assessment in 2014 and has consistently identified climate change, including extreme heat, as a threat to military readiness, infrastructure, and geopolitical stability. Military installations across the Southwest and Southeast are experiencing heat conditions that limit outdoor training activities and stress base infrastructure. Multiple installations have implemented heat restrictions that reduce operational tempo during peak summer months. The security implications of heat-driven instability in other countries, food insecurity, water stress, migration pressure, state fragility, are incorporated into threat assessments at the Defense Intelligence Agency and in regional combatant command planning. The National Security Council's Climate Working Group has included extreme heat scenarios in exercises and planning processes. This institutional engagement with heat as a security issue is significant because national security framing sometimes succeeds in mobilizing political attention and resources where public health and environmental framing does not. The bipartisan legislation that has historically funded defense infrastructure and readiness has proven more durable across political cycles than environmental legislation. And framing heat adaptation investments in terms of military readiness, supply chain security, and geopolitical stability represents a potentially more politically viable pathway than framing them exclusively in environmental terms. The specific experience of Phoenix, Arizona, the largest American city in the hottest and driest region of the country, functions as a kind of extreme case study in what heat adaptation at the municipal level looks like when it is taken seriously and what its limitations are. Phoenix has implemented a comprehensive heat response program that includes a well-publicized network of cooling centers and heat relief stations, a dedicated office focused on heat mitigation, a tree planting program targeting low-canopy neighborhoods, cool pavement pilot programs on selected streets, and a public communication campaign that has substantially increased heat illness awareness among residents. The city has also invested in street shade infrastructure in commercial and pedestrian corridors. The results are genuinely positive in terms of reducing heat-related emergency room visits and deaths relative to what they would otherwise be. But they also reveal the scale of the challenge. Despite these investments, Phoenix still records dozens of heat-related deaths annually, with Maricopa County, which includes Phoenix, recording 265 confirmed heat-related deaths in 2022, the highest single-year county total in American history. The gap between what Phoenix has accomplished, which is meaningfully more than most comparably hot American cities, and what would be needed to fully protect its population against the heat of a 2 or 3 degree warmer world, illustrates the fundamental scale mismatch between current adaptation efforts and future climate conditions. The frequency and intensity of heat events in America is projected to continue increasing regardless of near-term emissions decisions because of the thermal inertia already accumulated in the ocean atmosphere system and the long atmospheric lifetime of carbon dioxide already emitted. This committed warming, the warming that will occur even under immediate and dramatic emissions reductions, means that the heat adaptation challenge is not contingent on the outcome of emissions reduction debates. It is a certain requirement, the scale of which is determined by how much additional warming occurs on top of what is already locked in. This framing matters for policy because it separates the adaptation conversation from the politically polarized mitigation debate in a way that could enable broader political support for adaptation investment. Every American who experiences extreme summer heat, regardless of their position on climate policy, regardless of their beliefs about the causes of warming, has a concrete material interest in infrastructure that keeps them safe during heat events, in emergency systems that respond effectively, in housing that remains habitable, and in workplaces that protect them from heat illness. The politics of heat adaptation can in principle be organized around these shared material interests in a way that transcends the culture war framing that has made mitigation policy so difficult. Whether American political institutions are capable of organizing around those shared interests at the scale and speed the situation requires is a question that the data and evidence about the physical trajectory of American heat make increasingly urgent with each passing summer. The specific historical moment in which this transformation is occurring matters for understanding why the response has been so inadequate relative to the scale of the problem. The United States is in the early decades of a multi-generational transition in its energy system, its built environment, its agricultural practice, and its relationship to a thermal environment that is changing faster than the institutions responsible for managing it have adapted to. The federal government, The states, the cities, the private sector, and civil society are all simultaneously recognizing the scale of the challenge and struggling to mobilize responses at the necessary scale within political and economic systems that were not designed for this type of slow-moving, compounding, systemically distributed crisis. The institutions that have proven most effective at managing acute crises, emergency management systems, public health emergency frameworks, military mobilization, are not well suited to the chronic, incremental nature of heat transformation. The institutions that are better suited to managing chronic, long-term challenges, urban planning, building codes, public health departments, agricultural extension systems, have been systematically underfunded and underempowered over the past several decades. The mismatch between the institutional tools available and the nature of the challenge being faced is one of the most fundamental obstacles to adequate response. And addressing it requires both the unglamorous work of rebuilding institutional capacity and the political leadership to make the case that this slow-moving transformation deserves the sustained attention and investment that more dramatic crises automatically generate. The temperature records that fell across America in the summers of 2021, 2022, 2023, 2024, and 2025, each year adding to a list of broken records that grows longer and encompasses more of the country, are not aberrations interrupting a stable baseline. They are the baseline shifting. The question embedded in the phrase, "only the beginning," is not whether America will experience heat events worse than any so far recorded. The physics makes that answer unambiguous. The question is whether the response to what is already happening and to what is coming will match the scale and urgency that the evidence demands. In emergency systems, in healthcare capacity, in housing standards, in worker protections, in urban infrastructure, in energy systems, and in the political institutions that determine whether any of these changes can be made fast enough and equitably enough to protect the people who are most exposed to the transformation that is already well underway across the American landscape.